Previously, we saw the relationship between the polar form of a complex number and trigonometric functions. So that will give us a way to rewrite our well-known trigonometric functions. For example, we saw that e to the I t was equal to cosine t plus I sine t. But that means that e to the minus it is equal to cosine t plus I sine of negative t. Now, sine of negative t, or sine, is an odd function. So sine of negative t is actually minus sine of t, and we can write it that way. And then if we add these two equations together, we get that e to the it plus e to the minus I times t is equal to 2 times cosine t. So solving for cosine, we get that cosine of t is equal to e to the it plus e to the minus it all over 2. Now we can do something similar for sine. So let me take these two equations and copy them over there. And then instead of adding them, I'm actually going to subtract them. So e to the it minus e to the minus it. When I subtract them, the cosines cancel out. And then I get 2I sine t. So sine t can be written as e to the it minus e to the minus, or it, all over 2I. And so cosine and sine can both be written in terms of complex exponentials. Now it turns out that there are two more related functions. They're the hyperbolic trig functions. One is called cosh, or hyperbolic cosine. It's defined to be e to the t plus e to the minus t over 2. The other one is called the hyperbolic sine, or sinh, and that's defined to be e to the t minus e to the minus t over 2. So notice that neither one of them has an I in it. These are interesting functions, okay, because they behave a little bit similarly to cosine and sine. In fact, if you take the derivative of cosh of t, then you end up getting sinh of t. And I challenge you to work that out yourself using the definition. And then the derivative of sinh of t is equal to cosh of t. And so the derivatives are similar, except for the derivative of cosh of t is sinh of t, not minus sinh of t. If you're wondering where these names come from, right, cosine t and sine t, right, are based on the unit circle. They come from the idea of x squared plus y squared equal to 1. I can let x be cosine, y be sine, and then x squared plus y squared is equal to 1. That's the unit circle. Well, the hyperbolic trig functions come from the idea that x squared minus y squared is equal to 1. That's going to be the unit hyperbola instead of the unit circle. Okay, we're going to use these hyperbolic trig functions in a couple contexts in the near future, so it's good to have those definitions. Okay, let's move on to one last example, and that involves derivatives with complex numbers. So I want to look at what does e to the zt look like. So what does it look like when I do e to a complex number times, say, some time t? Well, that's going to be e to the a plus bi times t. So that's e to the at times e to the I times bt, using those exponential rules. Well, that's going to be e to the at times cosine bt plus I sine bt. And so that gives me another way to write e to the zt. If I want it to be a true complex number, maybe I'm going to write it as e to the at cosine bt plus I e to the at sine bt, so that I have its real and imaginary part. Now, what happens when I want to take the derivative of e to the zt? Well, what I'm going to do is I'm going to take the derivative, assuming that I can take the derivative of the real part on its own, and then I can take the derivative of the imaginary part on its own. So I'm going to assume that that rule applies, and that rule does seem natural. Okay, so when I do that, I'm going to have to do a lot of product and chain rules. So I'm going to do this as efficiently as I can. But the derivative of e to the at is going to be a e to the at, and then I'm going to leave the cosine of bt alone, plus I'm going to have e to the at times a minus b sine of bt. And then I'm going to do plus I times, taking the derivative, I'm going to get a e to the at sine of bt. And then I'm going to add to that e to the at times b cosine of bt, finishing out that product rule. Now, to make things more simple, I'm going to factor out an e to the at. And then I'm going to try to combine like terms. So in fact, actually, I'm going to factor out e to the at times cosine of bt. So that will leave me with an a plus b times I. Okay, so let me underline some things. So I'm going to have a e to the at cosine bt, and then I'm going to have I times e to the at b cosine bt. And those two are going to combine right here to give me e to the at cosine bt times a plus bi. Okay, so now I want to combine the things with the sine. So let me see if I can combine these two things. So that's going to give me, let's see, we're going to do e to the at times sine bt. And then what is left over is going to be, let's see, I times a minus b. Okay, so that's going to be the red part right there. Okay, so let's see what else that I can do. I'm going to keep this first part the same. So I'm going to write this as e to the at cosine bt times a plus bi. And then a plus, and now I'm going to factor out an I. So by factoring out an I, what's going to be left is going to be e to the at sine of bt. And then factoring out that I, I'm going to get a plus bi, because the I times the bi will give me the -1. Okay, so looking at that, I have, let's see, a plus bi times, I'm factoring that out, and then what's left, let's see, so I have e to the at times cosine of bt plus I sine of bt. So really, that's going to be, looking at what I had above, okay, it's going to be z, and then e to the at cosine bt plus I sine bt, that's actually e to the zt. And so yes, I just proved to you that d dt, the derivative of e to the zt, is ze to the zt. And you knew that before, but you knew that when z was a real number. And now I've shown to you that it's true when z is a complex number.